This is surface area of revolution.
I'm video conferencing with my class, so don't try to walk through the kitchen or dining room butt naked or anything, okay?
Okay, let's see what is the idea.
Let me take out the trash.
Suppose I have a curve that looks like this. Now then surface area of revolution that we are looking for is the surface area of this solid if we revolve them with respect to x-axis or respect to the y-axis later. So it looks like approximately like this. So what's the area of this figure here if I revolve that with respect to the x-axis? That's what we are going to do. Okay, now we will start by doing the following. Let me erase first. We will start with the original curve that we have earlier. And let's say this is the curve. Now we want to find the area when I revolve that, but let's first look at this section. One of the section, I take one of the section, let's say I do this kind of cut here. Okay, so we will be dealing with this segment, which I will revolve with respect to x-axis. Now, when I revolve that with respect to the x-axis, then it looks like a shell, right? It looks like a shell. Now, what is the area? The question is, what is the area of this shell? Now, once we find the area of this shell, then we can integrate the area of this shell, integrate the area of the shell, each shell, and that will give us the area of revolution. Okay, now the thing is how to find the area of this shell. Let's see the following. I will first, again, I get this part here. We know from 8.1 the length of this segment is ds for sake of simplicity. Now, when I revolve this, the shell looks like the lateral area of a can. So it's basically the area will be the circumference of this circle here. If we see this from sideways, you see that this is like a circle. If we see that from this point of view, right? It's a circle, okay, and that circle, oops, that's not nice. That circle has radius y. This y here. That circle has radius y. Okay, so that the circumference is 2 pi y. Now the area of that shell, therefore, is 2 pi y times ds. So where's the ds in this picture here? The ds is here. This is the ds. Okay, now then the total area of the shell will be 2 pi y ds. Now, suppose I need to find the total surface of total surface area of revolution from A to B. Then the area of revolution will be equal to integral from A to B, 2 pi radius times ds. That's the formula. Okay. Now the thing is, we need to apply this though. We need to apply this. We will use this formula first, the one that we revolve with respect to x-axis. Suppose, for example, I pick question from our book. Let's say I pick this question here. I see example 2 from the textbook. Example 2 from our textbook. Y equals to x squared. And then from x equals to
0.
From 1, 1 to 2, 4, but this time they revolve rotated about y-axis. If we rotate that about y-axis, then what will happen? Okay, so let's see first. The curve approximately looks like this. Okay, and we want to rotate with respect to the y-axis though, not x like we did earlier. Okay, so the shell that we get later on will look like this. This is one of the shell. Now, then what is the area of that shell? Then that will be 2 pi times, what is the radius here?
Y.
No, that's not y.
Oh, X.
That's the x. That's our 2 pi x times ds, right? Okay, so that's the area of the shell. So the total area will be integral from the y equals to what? To y equals to what? From y equals to 1 to y equals to 4. Y equals to 1 up to y equals to 4. Okay. Now then, this will be integral from 1 to 4, 2 pi x square root of 1 plus dx dy being squared dy. That's if we want to do it that way. This is my ds. This is my ds. This is my ds. Okay, but I can also do it another way. If I want to use dx here, then my integral will be from 1 to 2. 1 to 2, 2 pi x square root of 1 plus dy dx quantity squared. Now, in this case, this is my ds. You will see I will do the second integral instead of the first one. You can do the first one also, okay? But I will do the second integral. Why I don't want to do the first integral? Because of this thing here. This is x, while this is dy. So I need to change this x into the function of x as a function of y. So if I proceed from that integral, that's integral from 1 to 4, 2 pi
Wait, what?
square root of y, square root of 1 plus dx dy. So dx dy equals to 1 over 2x.
Professor,
Now, yes?
what changed when we integrated from 1 to 2 instead of 1 to 4?
The variable of integration.
Okay, I know that, but like, what's like, if I were to get that problem, what is that part of the problem or is that a separate way of doing it? I got lost.
There's two different ways to do it.
Oh, okay. And why
Yeah.
choose one over the other?
Huh? We can do, you can use either one of them, but usually one of them is harder to do, so you need to use another one.
Okay, depending on the problem.
So let's see if I continue there. This will be 1 over 4y dy. Now this is not integrable. It's so hard to integrate. Okay, such that I will proceed with this one here. This is integral from 1 to 2 pi. It's already dx, so I don't need to change this x here. Okay, 1 plus dy dx, that's 2x being squared dx. So then we can integrate this ourselves. Okay, now here's the thing. The purpose of what I do in this example here is the following. It's more about the setup. What happened here if I revolve that with respect to, when I revolve that with respect to the x-axis, then the radius will be y, right?
Yeah.
The radius will be y. When I revolve that with respect to the y-axis, the radius will be x. This is my radius. Okay, now then, depends on how the function being given to us. Example 2 is a great example to show you that for each type of surface area of revolution, you actually have two ways to do it. Okay, either you deal with the dx or dy. Now, how do I know which one to use, Thomas? By experience. But sometimes if you do one of them and then you kind of like, oh, you know what, this is so hard to do, try another one. Now, let's do the actual problem from the book. I will start with the easiest possible, of course. Number 6. Number 6, we have finds the exact area of the surface obtained by rotating, so the revolution with respect to x-axis of this curve. 9x equals to y squared plus 18 for x between 2 to 6. So again, let's say this is our coordinate system, and let's say this is the curve. I think the curve actually looks like this, quite similar to this. It looks like that, where the vertex is 18,0. something not right here. My bad, my bad. Give me a second. Give me a second. My graph is wrong. No, actually not 18,0. Now I see. It's supposed to be 2,0. 2,0. When x equals to 2 and the y equals 0, it will make it. Okay, then I want to revolve this with respect to the x-axis. So let me pick one segment there. Let's say I pick this segment. What is the length here?
ds.
That's ds. And the radius is?
Y.
Y. So the area of the shell will be 2 pi y ds. Now then the surface area of revolution will be integral from what x to what x? From x equals to 2 to x equals to 6, right? From 2 to 6 of 2 pi y ds. Okay, but because my interval is from 2 to 6 for x's, right? That's for x. Then I need to change this dx here. I need to change this dx here into something dx. Into something dx. Integral from 2 to 6 2 pi y square root of 1 plus dy dx being squared dx. Now let me slow down here. Is it okay? The reason I make it dx because I want to integrate from 2 to 6, which is x equals 2, x equals 6. Right? That's why then the variable of my integration is supposed to be dx. Now, I bump into an issue here. Y is a function of x, so I need to change this y too. So that's integral from 2 to 6, 2 pi, what is my y?
Root 9x minus 18.
Root 9x minus 18. And then how about the one here? That's 1 plus, this is 9 dx equals to 2y dy. So dy dx equals to 9 over 2y. So that will be, I don't have enough space. I should have more space. 9 over 2 square root of 9 over 2 square root. What is my y again? 9x minus 18, like this. Now that's my dy dx. So if I square it, I get 81 over 4 times 9x minus 18 dx. So this y becomes this guy. And then this dy dx in that radical thingy becomes this guy. So far I only did substitution. Now, what I will do next is, let me, you know what? I think I want to multiply this in. So I get square root of 9x minus 18 plus 81 over 4 dx. Integral from 2 to 6, 2 pi square root of 9x minus...
You so smart, NGI.
Repeat again. I think this is plus 9 over 4 dx. Let me factor the square root of 9 out. It becomes integral from 2 to 6, 2 pi 3 square root of x plus 1/4 dx. Now then from here, I think you can integrate it yourself anymore. Basically, this is what you need to integrate. Is it okay?
Mm-hmm.
Now, how would you integrate that? Can I leave it to you?
Yeah, I think we could.
U equals to x to the x plus 1/4.
Yeah.
So du equals to dx, right?
Mm-hmm.
Okay, so this is 6 pi integral 9 over 4 here. This is 25 over 4. That's u to the power of 1/2 du. Boom, 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 boom. Now you see, my point is this. Anything from here and on is technique of integration. What we learn in this section is only this part. That's what we learn in this section. How to integrate that, it depends on how good you are with your what you have learned so far. Okay. Now, on the other hand, I want to quote this part here. I want to quote this guy here. I may be able to do it another way. Notice that I changed my y into square root of 9x minus 18. Notice that I changed it this way. That's because I use dx. Suppose I want my variable of integration becomes dy, then what will that be? Let me do it here. Surface area, therefore, equals to integral 2 pi y square root of 1 plus dx dy being squared dy. Okay, and then let's take a look. When the x equals to 2, what's the y? When x
0.
equals to 2, the y is 0. When x equals to 6, the y is
54. 2.
Hmm?
Oh, wait. Square root 2?
Hold on. When x equals to 6, that's
56 equals
4.
14.
Y equals to 6 also? Okay, so my integral now, if I make it in terms of y, that will be from 0 to 6 of 2 pi y of that. Now, earlier we already compute actually the derivative of x respect to y up there. So you see from here, if I quote from here, dx dy equals to 2y over 9. You see that?
Mm-hmm.
Okay, then when I square it, it becomes, 4y squared over 81. And then I think I will do substitution. So let my u equals to 1 plus 4y squared over 81. Then my du will be 8y over 81 dy. And yeah,
dx dy equals 2 over 9 squared. Oh,
so when my y is 0, this is 1. When my y is 6, oh wow, 4 times 36 over 81. Reduced by 9, this is 4, reduced by 9, this is 9. So that's 16 over 9. Plus 1, that's 25 over 9. So this is y dy, this is my y dy. So that will be 81 over 8 du, and then I have u to the power of 1 half. I think this one is integrable. Okay, let's do some integration. How many of you willing to do the blue integral? Half, half. Okay, some of you do the blue one and some of you do the black one.
okay, I'll do the blue one since I already got far on that one.
Yeah, okay. Basically, half of you do the blue one, the other half do the black one. Let me do the black one because it looks uglier. So this is 81 over 4 pi out. And then integral, that's 2 over 3 to the power of 3 half 1 25 over. The answer is 49 pi. That's what I expect for us to get on the blue part. This is 6 pi integral times 2 over 3 u to the power of 3 half from 9 over 4 to 25 over 4. That's 4 pi times 5. 125 over 8 minus 27 over 8. 98 over 8 here. That's 49. That's also 49 pi.
With both of them being 49 pi, what exactly does that mean?
It means in this case, especially in this case, you can use either way to compute it. Either your variable of integration is dy or your variable of integration dx. Either way, it's fine. I mean, it's actually always okay to do it either way, but usually one way is harder than the other one. Like in this case, if you think about it, it takes me less time actually to set up an integral when I do the variable is dy. While when the variable is dx, the setup is easy, of course, but then to integrate that takes me a longer step. Do you see that?
So what do you prefer?
Well, I prefer the one doable.
I came up with 24 pi. I don't know what I did wrong.
So the question, so Thomas, which one you prefer?
125 minus
The one,
27.
the one that is doable, because there is big chance that one of them work, the other one doesn't work. The example I show you here, both of them work.
Okay.
Okay.
Yeah.
Now,
Thank you.
on the other hand, it also means the following: there's a chance that when you set it up, of course, you need to see if you make any algebraic mistake. Okay, but suppose we don't have algebraic mistake, and it turns out to be quite difficult to do, then try to shift to another point of view. Let's see another one. Let's see number 10. Let me ask you to do that one. Number 10. Y equals to x cubed over 6 plus 1 over 2x. Again, we will revolve that with respect to the x-axis, while the x value is from 1/2 to 1. Let me ask you to set up the integral. I will help you with the derivative. Yeah, I think this one you want to use the area of the shell is 2 pi y ds, where the ds is square root of 1 plus dy dx squared. And the y will be that ugly guy. Okay, let me give you 5 minutes to try to integrate this. So the surface area of revolution will be integral from 1/2 to 1 2 pi y, which is x cubed over 6 plus 1 over 2x square root of 1 plus dy dx being square dx. My suggestion before you actually write that integral, try to find what will this be first. So find out what is this first.
Okay.
Let me give you maybe 5 minutes just to get the feeling on how to approach this. So this is 1 plus x squared over 2 minus 1 over 2x squared being squared. And then if you work it out, I believe you will get 1 plus dy dx being squared is equal to x squared over 2 plus 1 over 2x squared being squared. Is it right? Such that the square root of that, is equals to x squared plus 2 plus 1 over 2x squared. Now then go back to my integration. This is integral from 1/2 to 1. Let me pull the 2 pi out. I get x cubed over 6 plus 1 over 2x multiplied by x squared over 2 plus 1 over 2x squared dx. So basically the 2 pi, I bring it out. Okay, and then the square root here now becomes this. Now, what do you do from here, by the way? We will FOIL them. Okay, we'll FOIL them. So x to the 5th over 12 plus x over 12 plus x over 4 plus 1 over 4x cubed dx. That's what you need to integrate. Okay, let me go one more step then, but then anything from here is supposed to be something you can do on your own. X to the 6 over 72 plus x squared over 24 plus x squared over 8 plus, should be minus, x to the -3 becomes -2 becomes -4. So 1 over ax squared. Oops. From 1/2 to 1. Okay, then from there you just plug in numbers. Now that's for number 10. But Thomas, do you think this question is too hard? No, because what we learn here is just to set up. Okay, in this section, we only learn to set this up, and everything after that, we rely on how good you are in your technique of integration. Okay? Now, let's go on. The following question makes you think, number 12. Number 12, we still revolve with respect to x-axis. However, the equation is given by x equals to 1 plus 2y squared, where the y moves from 1 to 2. So the curve looks like this. Okay, the y is from 1 to 2. Okay, but we will revolve that with respect to the x-axis. This will be revolved with respect to the x-axis. So the area of the shell will be 2 pi y ds. However, the domain of integration later on will be in terms of y. Now you figure out how to set it up.
Oh, because it's going to be spinning around there. Okay.
So dy will be 4y. That will be 4y. So dx dy squared will be 16y squared. When I add 1, that's plus 1. So my ds, this is square root of 1 y squared, square root of 1 plus 16y squared. The surface area will be integral from 1 to 2, 2 pi y square root of 1 plus 16y squared dy. Okay, I think you can integrate this yourself. I will just go ahead to the next example. You go on yourself, you use u equals to 1 plus 16y squared as a substitution. Okay, now that's for number 12. Let's go back even further. How about if I have number 14? Number 14, this time the revolution is with respect to y-axis. Number 14, y equals to 1 minus x squared, where the x is from 0 to 1. Actually, I don't need the left hand side. But this time we rotate that with respect to the y-axis. So let's say this is the segment. I rotate that with respect to the y-axis. What is the radius?
X.
The radius is x. So the area of the shell will be 2 pi x ds. Okay, you try to work it out. Just set up the integration. Let me give you maybe 2 minutes to set up the integration. Maybe 3 minutes. Then you can do 1 or 2 more extra steps from there. Okay, let me start. This is dy dx equals to 2x. So dy dx being squared is 4x squared. If I add 1 and the square root of 4x squared plus 1. So the surface area of integration will be integral from 0 to 1 2 pi x square root of 4x squared plus 1 dx. Okay, that's the setup. And then going on from there, I will use u equals to 4x squared plus 1. So du equals 8x dx. Okay, now I think you can go on from there further yourself. Now that's for 8.2. The suggested homework here will be 8.2 suggested homework will be from number 1 to number 15. Just do the odd ones again. And even for number 1 and number 3, just do the setup. For number 1 and number 3, number 1 and number 3, just do the setup. Okay, the emphasis will be on the setting up. And so in your next test, you will see that beside testing you on technique of integrations, including those improper integrals thingy, this 8.1 and 8.2 implicitly requires you to know how to do in technique of integration. On the top of that, you need to know how to do the setup. Okay, now that's for this 8.2. Let me go on to 8.3. 8.3 consists of two major parts. Let me call that 8.3a.
I'm sorry, really quick, what was the homework again from 8.2? I'm sorry.
From 8.2, number 1 to 15 on.
Okay, thank you.
8.3a, the one that I will do today is hydrostatic pressure. Okay, and then hopefully I can do extra to the second part, touch base a little bit about the second part, but we will spend more time on this hydrostatic pressure. What is hydrostatic pressure? It will be as the following. We are interested in, how to explain it better? Suppose I have, let's say I have a pool. Let's say I have a pool or a box, let's say for now, a box, which I fill up with water. I fill up with water, water is blue color, okay. Let's say this is the water. Okay, now we have water and we are interested in finding how much pressure being experienced at any point inside the water. Now the way we develop that will be as the following. The way we develop that will be as the following. First, let's take a look on the pressure. The formula for pressure in physics is equal to the amount of force applied on a certain area. While, so let's say I want to find what is the pressure experienced at any point on the base of this pool or this box here. Then the pressure at any point of the base of the pool will be equal to the amount of force divided by the area of the base.
1 second.
Okay, now what is the amount of force? The amount of force will be the weight of the water in this case. Okay, now, but the weight of the water is equal to the volume of the water multiplied by density. Which is equal to the volume of the water, of course, equals to the area of the base times the height of the water times density over the area. Actually, I think I'm missing something. I'm missing the gravity. Oh, I'm good. This density is actually rho. It's actually rho g. Okay, so then when I divide, I cancel. Then the pressure experienced at this point. The pressure experienced at this point. This is any random point at the base of the pool that's equals to the height or the depth. This is the height. How far that point from the surface of the water or any other liquid multiplied by the density. Okay, now our textbook, if you take a look, they say that the P equals to D times density, where the D is the depth. How far is the point from the surface of the water? And the delta here is the weight density, which is rho times G. Maybe I write it this way. The delta is weight density. The rho is mass density. And G is the gravity.
Oh, mass density. Oh, wait.
Okay.
Equals mass.
Now, this P is the one we call hydrostatic pressure. Now, if we ask what is the hydrostatic force? Hydrostatic force, then it refers to the force that applies to all the green region here. Okay, that's so you can imagine the following. Suppose you need to carry this water from below. If you have to carry this water from below, okay, then how much force you need to exert so that the water is stable? It's not moving.
Wow.
Okay. Now, that's hydrostatic force. Now, what is hydrostatic pressure? Hydrostatic pressure is the amount of the pressure that being experienced at any point of the base here, at any point of the base. Now, as you can see, hydrostatic pressure is actually independent of, the shape of the container. It's just depend on the density and how deep it is from the surface of the water. Okay, now N.
Can you repeat that?
The hydrostatic pressure depends only on the density of the water and how deep is the position we're dealing with. While hydrostatic force is basically the integral of that pressure over the area. And that's hydrostatic force. Okay. Now let's say, for example, just for to make it easy for us, let's do an example here. Let's do an example. Suppose I have a box filled up with water, and the dimension of the box is 4 meter by 6 meter, with the height to be, let's say, 5 meter. Okay, so let's say this is 4 here, this is 6 here, and this is 5. And let's say we fill it up with water. We fill it up with water. Now then, let's first ask, what is the hydrostatic pressure experienced at the bottom of the water? Find hydrostatic pressure at the bottom of the box. And again, let's fill up with water, okay? The word hydro simply means liquid, something liquid. The word static here means the liquid is not moving. You see? Okay, so if you have this water and it's stable, then what is the hydrostatic pressure experienced at the bottom of the box? The hydrostatic pressure equals to the depth, how deep the point from the surface, multiplied by the weight density, which is D times rho times G. What is the D?
Depth.
Which is, in this
5
case,
meter.
is 5 meter. How about the rho? The rho of water, the density of water, the mass density of water is 1,000 kilograms per cubic meter. Okay, and then the G is 9.8 meter per second squared. Now then this will be, what is this, 5,000, let me just write it this way, 5,000 times 9.8 kilogram over meter second squared. Okay, now this guy is usually called, this unit is usually called Pascal. So this is equal to 5,000 times 9.8, whatever that is, times, the unit is Pascal, PA. That's the unit for pressure. Or you can say, if I compute this, this is, I believe, is 49,000 Pascal, or equals to 49 kilo Pascal. Now, in my class, I will just let you leave the rho and g as rho and g. You don't need to plug in numbers. Why?
Oh,
Because
cool.
the reason is it is possible that the liquid we use later on is not water. And if, for example, we deal with salt water, the sea water, then the density is higher than regular water, right? Okay, and suppose one day you go to the moon, the gravity there is different. Okay, so we will just leave it as rho g. So the pressure, hydrostatic pressure here will be just 5 rho g. That's how you say it. Okay, so in my class, you will say 5 meter rho. I'm sorry, 5 rho g meter. 5 rho g meter. Why I cannot get the eraser?
Okay.
But the unit is not meter though. The unit is not meter because in rho you have their own unit, the g you have their own units, right? Okay. Or maybe as a number, let's just for the number, then we write just 5 rho g. Now suppose, with this said, what is hydrostatic pressure in our daily life? It feels like as the following. Suppose you dive under the water, you dive, and the water is pure water. Suppose your ear is at the depth of 5 meters. The pressure that your ear experience is actually 5 rho g, which is quite heavy already. The pressure your body experience at that depth is 5 rho g. That's 49 kilopascal. Is it okay? Now,
Yep.
I hope that explains why that human usually are not allowed to dive deeper than how many? Like 300 meters without, I'm sorry, not 300. I think 30 meters without any tool. You won't be able, your ear, at least, your ear will not be able to handle the pressure. Imagine the water above you will try to crush your body, right? Such that if you want to go a lot deeper, when you imagine if you have a very deep sea, right? You have a very deep sea. Let's say this is the sea, and then you try to dive in. Okay. Now the pressure that you experience here will be equals to how deep you are multiplied by rho g. Are you with me? Okay. Now suppose you have Thomas there swimming. Then the weight of the water above him, will try to crush him. You basically need to take care the density multiplied by the depth of that water and apply that on your body. That's why if you dive way too deep, then your body will get shrink.
We'll get what?
Your body will get shrink,
And,
get smaller. Your body volume will get smaller
okay.
because what? The pressure, right? The water actually pressuring your body. Okay, so hard such that if you try to go even further further down, eventually your body will get crushed. And among our body that get crushed first, usually our eardrum or the mucosa, whatever that you call it, some kind of membrane inside of your nose. You see what I mean?
Yeah.
Now, that also means the following. If you have some fish living in very deep sea, they get used to with that pressure. Okay? If you suddenly bring this fish up, you see, the fact that that fish can survive in such a deep, under a deep ocean, it means the pressure, the internal pressure of that fish must be so high to be able to sustain the pressure, right?
Yeah.
Now, once you bring that fish up here at the surface, the internal pressure of that fish is a lot higher than the pressure of the air once it is in the surface. So what will happen to that fish?
He'll explode.
That's right, it will explode. That's right, it will explode. Okay, so that's why fish, the deep ocean fish cannot survive if you bring it to the pool. Why? The pool, however deep it is, the pressure will not be as much as how deep it is. I mean, let's say your pool is 10 meter deep, while that fish is living under like 500 meters under the water. Then the pressure it feels is actually 50 times less, right? With that kind of difference pressure outside and inside of its body, the fish will explode. While we, because we get used to live up here, right? Okay, will you push me down 500 meters? If you push me down 500 meters, then my body basically being crushed by a pressure more than 500 times. Okay. Good enough if you can go that deep. Okay, good enough if you can go that deep. By the time you reach that deep, your body already crushed. That's why if you want to go even further, more than 50 meters, then the pressure, the shell, whatever tool you use, need to be able to sustain that pressure. Now, to go even further, imagine if you have submarine. Then every point on that submarine, especially at the shell of that submarine, should be able to sustain the pressure, which is D times rho times G. And don't forget, the rho is not the rho of the water, it's seawater, right? Now, the pressure will try to crush this submarine from every direction. I hope now you understand that you cannot use a regular, if you look at submarine, there's no place in that submarine actually using a glass. Do you realize that? You cannot use glass because glass cannot hold too much pressure. You need to use some kind of like very strong steel, right? So if one day you becomes a military submarine engineer, this is one thing you need to consider. Okay, that's just some side story. Let me bring you to what we want to discuss here actually. Let me erase this first. Oh, sorry. Going back to this question that we have earlier, okay, Suppose I choose a point not that deep. Suppose I choose a point not that deep, but that point is actually on the right-hand wall here, and it's only 3 meters deep. So part B, find the hydrostatic pressure at the wall 3 meters from the surface. Then the hydrostatic pressure will be the depth, which is 3 meters, times weight density, which is 3 rho g, and that's all you need. Okay. Now, what we will have after this will be a lot harder. So let me give you a break. We come back at 6 o'clock. No, I'm sorry. 6:05. Let's take a break. We come back at 6:05, and that's where life will become harder for you. Okay, see you later.
Okay.
We'll get the we will get a bit harder now. Let's see part C. Let me copy that graph first. Let me copy this graph. Let me copy this graph. So that we have a better point of view down here. Okay, suppose in part C, I am interested to find hydrostatic force at the bottom of the pool. Basically, that will be the green area. Now, notice that hydrostatic force is equal to the pressure multiplied by the area. Okay, the pressure multiplied by the area. The thing is, in this case, every point in this region, this green region here, every point on this green region experience the same hydrostatic pressure. So the pressure we had earlier was 5 rho g. I just need to multiply by the area of the green region, which is 6 meter times 4 meter. That will be 120 rho g. Again, because any point in this green region has the same pressure. Now, the harder one. Suppose I want to find the hydrostatic force at the smaller wall. There are 4 walls on this pool. There are 4 walls on this pool. The smaller wall is this one here. This is the smaller one. These are the smaller one. They are the same rectangle. Okay, and the front, the back sides are the larger wall. Now, if I take a look on the smaller wall, that will be 4 by 5. This is 4 here, and this is 5 here. Now, the surface of the water is here, right? This is the surface of the water. Now, here's the problem. The problem is at different point, the pressure will be different. The pressure at this point here is equals to the depth at that point, which is different from if we choose the point here. It's another depth. You see what I mean? The only points that have the same pressure are those points that share the same depth. The point that share the same depth. At this line here, they all have the same pressure. Okay, so let me pick that up from here. The force here is equal to rho G times D times 4 dx, where the dx is basically the small thickness of that water there. Notice that, where do I get that for?
One of the sides of the wall.
That's the length of that strip. That's the length of that strip. Okay, so actually using this notation, this is supposed to be dF instead of F. Now, then the total hydrostatic force will be the integral of rho G, the depth, let me call that X, times the width of that strip, dx, and what is my depth from here? My depth from the depth of 0 meter down to 5 meter. From 0 meter, I go down to 5 meter. At the depth of x, the width will be 4. My x will be from 0 to 5. Okay, everybody, the setup is quite difficult. You will see that the hydrostatic force that we are dealing with will be integral of rho G times the depth multiplied by the width at that depth. The depth multiplied by the width at that depth dx. Okay, that's how we get that function. That's how we get that integral. Now to integrate that, that's an easy stuff. That's f equals to 4 rho g, those are the coefficients, right? And then times 1/2 x squared from 0 to 5. That will be 2 rho g times 25, that's 50 rho g. Now, once you are done with that, I will give you 3 minutes to set up the hydrostatic force at the larger wall. Okay, let me ask you to try doing that. It's supposed to be still easy though. Okay, because on the larger wall, let's see what's the larger wall. The larger wall is the one here. The one, which color do I want to use? Yellow, huh? The larger wall is here. This is the larger wall. Okay, that's the larger wall. So let me say it looks like this. It's too big. It's a rectangle such that the depth of the water is 5, yet the width of the pool is 6 meters. Okay, now let me ask you to compute the hydrostatic force of the larger wall, at the larger wall. And that will be integral rho g times, let's say the depth is x. Let's say the depth is x. What is the width at that depth?
X.
What is the width?
6.
6, that's right. Dx. Now, x will be moving from what to what? Your x will start from here down to here, right? Now, your x here is what? What is the depth? At the surface?
0.
0. And at the bottom of the
5.
At the bottom of the wall, that will be 5 meters depth. Okay, that's the setup, and I think if you integrate this, you will get 75 rho g. The type of questions you have here actually on the easy side, because notice that for any depth you choose here, the width is the same, it's constant 6, right? Now we come up to, what does this mean? What does this mean? This means the following. Remember the part C, that's hydrostatic force at the bottom of the pool, okay? Now that's basically the amount of force you need to exert if you try to hold the water from below. Oops. If you try to hold the water from below, you hold it, right? How much force you need to exert such that the water stays constant, like not moving, okay? Then according to our computation is 120 rho g. Now, then what does the part D mean? The hydrostatic force at the smaller wall. It's like how much force you need to push on the smaller wall such that, suppose the wall is actually made of certain kind of, let's say certain kind of steel, right? Okay, now how much force you need to hold that that sheet of steel such that the water is not spilling out. You see? Okay. Now I hope then you understand that for us to build, you cannot really build something so tall with, and then the water so deep. The wall here has to be very strong, especially at the bottom. Especially at the bottom. Do you see my sketch here? especially at the bottom. In other words, like this: if I have a very big wall, a very tall wall, and then you fill with a lot of very high, tall water here, there's a chance that this wall collapse because the force of this water applied on this wall. You see what I mean? And
Yeah.
when it collapses, it's usually collapse starting from the bottom, because that's where the pressure the highest. You see, the pressure not really great at the top here, but it will actually break it at the bottom. Okay. Now, the hydrostatic force that I'm talking about here is how much force we need to apply to the whole small wall such that the wall is intact. Okay, and hydrostatic force at the larger wall is the amount of force this wall has to sustain to have the water actually well contained in that container. Now, our textbook have a good question, which let me modify it instead. Let me call this another example. Suppose I have a rectangle. I don't like this one. Let me use this one instead. And let's say the depth of this upside down triangle, let's say, is 10 meters, while the top also 10 meters. I try to make it easy for you. And then let me fill this water all the way almost at the top of this triangle. You can imagine this as a throat. Do I say it right? The throat? How to say this? Maybe after I draw this. Imagine if we have something like this. And let's say this is the container of your water. This is the container of your water. Okay, that's the container of your water. And then we want to compute what is the pressure at the side of this wall, this part here. We want to find the hydrostatic force on this wall. Okay, suppose the water is filled up to only 1 meter left. So this is 1 meter left. Okay, then if we think about it, then what is the depth of the water? How deep is the water? This is the whole thing is 10, but you fill it up until you have only 1
9.
meter left. That's right, that's 9 meters here. Okay, now then, suppose this is the depth of the water. Let's call this X. Then how long is the strip here? Now notice that at different depth, the length of the strip is different, right?
Mm-hmm.
Okay. Now, then how do we look at this? Take a look on when x equals to 0, that what is the length here?
9.
When x equals to 0, the width is 9. Okay.
Isn't it? Why wouldn't it? Well, I thought it wouldn't be the 10 meters though, because it's the top of the triangle.
But I don't feel the water all the way up.
Oh yeah, okay.
Yeah, I don't feel the water all the way up. Okay. And when
He leaves
x,
a meter at the top.
yeah, I leave 1 meter on the top. Okay. While at the bottom here, what is the depth?
0.
How deep is the water if we are at this
0.
point?
10.
10 or 9?
10.
At the bottom.
It'll be 9.
It's 9 from the surface of the water.
Oh, okay.
Okay, 9, the depth is 9, but how about the width at this point?
0.
0. Okay, now suppose this is x, then what will the width be? When the depth is x, then the width will be
9 minus x.
that will be 9 minus x. Okay. We're supposed to do the following though. We're supposed to do the following. We're supposed to do this kind of analysis here. So if this is 4.5, this is 9, then when this is x here, what will this width be? That's what we're supposed to do. Okay, that's what we're supposed to do. And to do that, we do proportion. 4.5 over 9. 4.5 over 9
Tanner,
equals to W over 9 minus
got a
x.
big envelope. And for some strange reason, it got sent to this address. Why is that? Okay.
Okay. Oh, by the way, this width supposed to be twice of that. 2 times. It's supposed to 2 times. Because when I draw it that way, the width is only half of the supposed width that we have. Right? Now then, when I play around with these functions here, you will see that W equals to 9 minus x. I hope you can see that, why it looks like that. No, I don't like that. Erase this. Don't use W here. Let me use Y instead. Don't use W here. Let me use Y. Because I don't want you to compute that Y with W. Let me use Y here. So this is Y. This is Y. So my Y will be Y will be 9 over x over 2. Now my width is 2 times y, therefore I get that 9 minus x. Okay, but remember the way we did it earlier is actually more intuitive, because when x is 0, it's 9. When x is 9, the width is 0. And you know that the width actually decreases linearly as the x increases. So if I go back to my setup, then how about the hydrostatic force? Hydrostatic force will be integral from what to what?
Zero to 9?
From 0 to 9, okay. Rho g, the depth is?
Nine minus x?
The depth. How
Oh.
deep?
9.
The depth as a function of x. The depth is x. The width is 9 minus x.
Oh, okay.
Okay. Let's do another example, and then we'll do problems from the book. Suppose, for example, I have, let's say this is the surface of the water, okay, and then I submerge a semicircle. Let me make it big enough. A semicircle like this, and the diameter let's say is 2 meters. So what is the radius?
One.
It's 1. Okay. Now then, I want to find the hydrostatic pressure, hydrostatic force of this plate. So you imagine this a plate that you submerge that down vertically. Okay, and how much force being experienced by this plate? Let's start. Let's say the depth is x. Let's say the depth is x. We know what is this here? What is the length of that solid red color?
1.
That's 1, that's
1.
right. So what is this here? That's square root of 1 minus x squared, right?
Yeah.
Okay, therefore, what is the width now?
2 times of that. So
That's
2.
right. So the width will be 2 times square root of 1 minus x squared. Now then, hydrostatic force experienced by this plate will be integral. X will be moving from what to what? From 0 to 1. Rho g. What is the depth?
2 times radical 1 minus x
The
squared.
deep. How deep it is? The depth. The deep is x.
X.
The width is 2 square root of 1 minus x squared dx. Okay. Do you think you can integrate this?
Let's see.
U equals to 1 minus x squared, right? So du equals to
X
x dx.
x squared. U equals 1 minus x squared. U equals 1
This
to
is
x.
0, this is 1, rho g. Make this du, and then u of 1 half. This guy will give me negative du. Okay, and then reversing the order of integration to absorb the negative, 0 to 1, rho g u to the power of 1 half du. That's rho g 2 over 3 u to the power of 3 half from 0 to 1. That's 2 over 3 rho g. Okay, now I go further. This is where the question, the way we set it up becomes more interesting. Suppose I change the situation a little bit. What we have earlier, we have water, and then the plate actually submerged in a way that it's the diameter is actually right. The diameter is actually right at the surface of the water.
Hey, can one of you feed them and put garlic powder in their food?
Huh?
Can you mute that first?
Over time, it makes them immune to fleas. It takes a while. That has to build up in their blood.
Demetria.
Oh, sorry.
Okay, now that's what we have earlier, in which that the diameter of that semicircle happens to be right at the surface of the water. Now I will change the situation. This time I have, let's say, the water here, but I submerge the plate 1 meter deeper. So the width is still 2 meters, okay? The radius is still 1. Okay, but I'm interested in finding the hydrostatic pressure, hydrostatic force experienced by the plate. Notice that this is the surface of the water. Now, suppose I make my x to be here. This is x equals to 0. Let's say that's my x equals to 0. And if I go x unit down here, let's say this is x, what will the width be? Now, according to our computation earlier,
Square root 1 minus x squared.
So this will be square root of 1 minus x squared, such that the width will be
2 times square root of 1 minus x1.
Okay. Now, here's the thing though. This x is, would you mind to mute that? Angel. Thank you. This x here is not the depth. It's not how deep it is. This x is actually the distance from this diameter to here. You see this? Okay. But the depth is actually what? The depth is actually
X plus 1.
Plus 1. Okay, so now when we go back to compute the hydrostatic force, then the integral will be from 0 to 1 rho g. What is the depth? X plus 1 to be more precise. Yeah. Okay, times 2 square root of 1 minus x squared dx. Again, this is the depth. And this is the width. So notice that my x is, my depth is actually a function of x. My width also function of x. Okay, but the width is not function of depth directly. Now, of course, how to integrate this? This is integral 0 to 1 rho gx 2 square root of 1 minus x squared plus integral 0 to 1 rho g2 square root of 1 minus x squared. I basically distribute against this thing here. visible one here. Okay. Now, the reason I distributed one of the main reason is because this is something we have done earlier. We compute this earlier. We compute that earlier. What's that? 2 over 3 rho g. Well, this one here, that's 2 rho g integral from 0 to 1 square root of 1 minus x squared dx. Now you need to compute that yourself further. I think I happen to be able to compute that fast enough. That's pi over 4. The reason is this is the area of a quarter circle with radius 1. Okay, now then you simplify that yourself. Okay, let's go on further. Using the same situation, similar situation, but I use another example. Suppose this time I have the water, let's say the water is, this is the water. Okay, and I submerge, oops, too much. I submerge my plate, let's say this way instead. I submerge my plate this way. This time, let's say the diameter, let me change that a little bit. This is 4 meters. Okay, and I submerge that 10 meters deep. Now, what we had before, we always do the reference point starting from this, the surface of the water. The reference line start from the surface of the water. Now you see in our last examples, that's not the case. Our reference points start from this diameter here. Now, I think that's what I will do also likewise in the last case. So I will start my reference from here. Let's call this x equals to 0. But then how far do I need to go up from there?
2 meters?
2 meters, that's right. So later on, my hydrostatic force will be integral from 0 to 2. Is it okay? My x will move from x equals 0 to x equals to 2. And then suppose I choose a random x, let's say this is x here, then what is this side here? Don't forget, if
2.
this is, what is this here? What is the length of this hypotenuse here?
2.
That's 2. So this will be square root of 4 minus x squared, right? Now then, what will the width of this strip?
2 times radical 4 minus x squared.
2 times square root of 4 minus x squared. Okay, so if I go back to my integral, that will be rho g, the depth, times the width dx. Is it right? Integral from 0 to 2 rho g. Now, how about the depth? If this is x, then the depth will be this part, right? Which is
10 minus x.
That's right, that's 10 minus x. And the width was 2 square root of 4 minus x squared dx. Okay, now how to integrate this, another story. But I think if I were you, I will distribute that. I will distribute that to be f equals to rho g integral from 0 to 2, 20 times square root of 4 minus x squared dx. That's if I distribute the 10, minus rho g integral from 0 to 2 of x, 2x square root of 4 minus x squared dx. Now here you will use u substitution, while the one here you can do, this is 20 rho g times pi, because that's area. This is the area of a quarter circle with radius 2. Okay, so that's equals to 1/2 times pi, 1/4 times pi r squared, that's pi. Okay, now the one on the right hand side, you need to do, work it out longer.
Can you scroll up a bit, Professor?
Scroll up.
Scroll up just a little bit. Yeah, the bottom is cutting off on mine. Thank
Oh, like this, huh?
Yeah, perfect.
Now, in the last around 10 minutes, let me do one more problem, but this time I will do problems from the book. For example, I pick problem number, which one is good? Maybe number 8. Number 8. So we have water here. This is the water. And then we have a plate that is partially submerged. That's a trapezoidal plate, partially submerged. The top is 4 meters. The bottom is 2 meters. Okay, it's submerged 1 meter depth. So the water only hit this part here. Now, this one question only, I can do with 3 different methods. Depends on where the reference line you want to do. Usually, I do reference line right at the surface of the water. Usually, but that may not be a good idea. Let me cut it off. So the part that's submerged in the water will be only this part, right? This is 2 meters here. This is 1 meter. Okay. And then this is 4 meters. This is 1 meter. Now suppose this is my x equals to 0. So if I go as deep as x unit, maybe I use red color better. Let's say I go as deep as x unit. What will the width be? What will the width be? Is it okay?
Mm-hmm.
Now, let's take a look on that trapezoid. Let's take a look at that trapezoid. Okay, if this is x equals to 0, and I go positive in this direction, then what will this x equal to?
1.
How about this x equal to?
The top?
Uh-huh.
1.
No.
They
If
both
this is 1, this will not be 1.
Oh, 2.
No, the 2 will be even deeper.
-1.
That will be -1, that's right. Okay, now then you see when x equals to 1, what is the width?
2.
When x equals to -1, what is the width?
4.
The width is 4. Now, because this is trapezoid, it means the width, when the further we go down, the width will decrease linearly. If we go up, it will increase linearly compared to x. Okay, so when x equals to 1, the width is 2. When x equals to -1, the width is 4. Then can we find the width as a function of x? 3 minus x. Now, if you have hard time with this, you can do the following. Okay, you can do the following. We expect W to be mx plus b,
Mm-hmm.
right? Okay, so what is the slope? The slope is 4 minus 2 over -1 minus 1.
Oh, yeah.
That's 2 over -2, that's -1. So W equals to -x plus b. And then I plug in either one of the coordinates, let's say 1, 2. The 2 equals to -1 plus b. That's how I get that my b equals to 3. So the width now is equals to negative x plus 3, or we can write it the other way around, 3 times x. So if the depth from that x equals 0 is x, then what is the width here? What is the width here?
Can you scroll up a little bit again? The bottom gets cut off for me. Thanks.
You can actually move that floating.
Yeah, I don't know how. Sometimes it's there, sometimes it's not.
You can move it up. You kind of like put your mouse there, and then you hold it, bring it up to the top.
Yeah, it's not doing it. It's locked.
Is it?
It's fine. I'll survive. We've got 5 minutes.
I have a question. Why is the depth x if we're using x like x equals to 0, x is equal to -1?
Oh, okay. Let me redraw that then. This is my trapezoid. My x equals to 0, I start from here. Now, do you agree with this first? If I start from x equals 0 here, then my depth x will be going to lower direction, going down. That's my depth. The longer this go down, the greater the depth, right? Which means if I go up, it becomes negative. Nora?
Yeah, okay. Thank you.
Okay. Now, therefore, yes, my x here later on will be from what to what?
One to -1? No. 1 to 0? Oh, 0 to 1.
From 0 to 1, because we don't need to call, we don't need to.
We're not concerned about the other part.
Yeah, we don't concern with the part not in the water. Okay, so we only concern with this one here, right? Okay, now then it will be rho g times how do we define the depth here?
X minus 1.
Is it x minus 1?
X.
Just x. And then for the depth x, the width will be 3 minus x dx. Okay. Now, I believe you can compute this yourself.
Yeah.
Okay? You can compute that yourself. I hope my next explanation does not confuse you. I will redo the same problem, but I use different approach.
Okay.
Suppose I have that trapezoid. Okay, this is 4 meters, this is 2 meters, but this time my line of reference, I start from the bottom. Let's say this is my x equals to 0. Okay, now how far do I need to go up to the surface of the water? X equals to what?
1.
X equals to 1. Okay, now so instead of in the earlier case, my x start from here going down. Right now, I don't do that. Right now, what I do is my x starts from here going up. Let's say this is my x. What will the width be? Okay, so when x equals 0, what is the width?
2.
When x equals to, how about the one here? When x equals to 2, what is the width?
4.
4. So when x equals to x, what is the width?
When x equals what?
When x at the height, if this is x here, at the level x, what is the width? X plus 2.
Oh, okay.
Okay, so because here's the coordinates, 0, 2, and 2, 4. What is the equation of the line? Well, because this is linear, right? The width actually increases linearly. So the y-intercept is 2, and the slope is 1. Okay, so this is the width, which is x plus 2, if I start from the bottom x there. Now, so hydrostatic force will be integral. My x will be moving from what to what?
From 0 to x plus, no. From
From 0 to 1.
0 to 1, rho g. Now, but when this is x, what is the depth? How deep it is? What is this here?
Is it
What is
1
this?
minus x?
That's 1 minus x, that's right. So this is 1 minus x, that's the depth. And the width will be x plus 2. Now, when you compute this, this is where you may get confused. When you compute this, the result you have here should be the same to the result you have here. The result you have here, should be the same to the result you have here, unless you set up one of them incorrectly. Okay? Now, with this example, I show you that there are usually more than one way to approach the problem. The first one, in the first way I use here, my level of water is my reference, while the one at the bottom here, the bottom will be my reference line. Yes. Who raised hand?
Why? So why would that be the confusing part, that the answers would end up being the same?
Because I use different method.
But ultimately, regardless of the method you use, I mean, you'd still expect the same outcome. I mean, we use different methods all the time, but
yeah. So what could happen is this though. I set it up one way, and then you set it up differently, and then you get confused why I do it this way.
Oh, okay. All right.
While you are actually, it is possible that your way is okay, you know, but in your test you will do it only with one way, right? When you compare with my solution, it is possible that my setup is different from yours, while the final answer look the same. You see what I mean?
Yeah, I understand. Thank you.
Now, to close this up, you see, from here, from my last example, my last work, I use my line of reference at the bottom of the trapezoid. Okay. Now, prior to that, my reference line is right at the surface of the water. Now, somebody may be crazy enough. No, not that crazy, but I mean, that's just an alternative. Somebody want to say, you know what, can I use my line of reference at the top of the trapezoid? Yes, you can. But if your x equals to 0 is here, then your integral will be from what to what?
-2 to -1? Or
Of course, the depth will go that way, right? Okay, will be from 1 to 2. If you go in this direction here. So 1 to 2, rho g, my depth will be x minus 1. Okay, because if this is my x, my depth only x minus 1. And my width will be, what will that? That will be, I think, 3 minus x. Or 4 minus x. I don't know. You figure out. I think is 4 minus x.
Huh?
That flavor is so ridiculous.
Which,
Yeah, okay. Now, when you integrate this, you should get the same answer too. So actually, in this couple minutes, I show you 3 different ways to do this same problem. So 3 different people may come up with different setup, but the final answer will be the same. Okay, that's where I will stop. On Wednesday, I will continue with 8.3, the second part, which is the center of mass and centroid. I wonder if they do the second moment thing. No, they don't. Yeah. And then after that, I think I will jump to chapter 10. Yeah, after that, I may jump to chapter 10, or I possibly go to chapter 12 instead. I will see in between what happened. But the lecture video I asked you to watch already include the center of mass thingy. So I think you can just continue watching those lecture videos and see you on Wednesday.
I have a question. Do you recommend for 8.3 to do numbers 3 through 11, or?
Actually, you can do 3 to 15, I think.
Okay.
Yeah, maybe I write it here. Suggested homework will be for 8.3a from number 3 to number 15. I think that should be enough.
Okay.
Okay.
And I have, sorry, one more thing.
That's okay. That's okay.
So
Don't worry about it.
I kind of noticed that for the